Hello everyone, good afternoon, and thank you all for coming. Our presentation today is about wearables and mobile devices. Why we need to worry when they both communicate with each other, and also we'll be looking at the spec. We've chosen the common protocols in use by wearable devices these days, that is Bluetooth and BLE. We'll take a look at the security offered by the spec itself, and we'll also see why the base security is necessary but not sufficient. Before we get started, a quick round of introduction. I'm Kavya, Senior Security Engineer with the New Devices Group at Intel. And I have here Chandra, my colleague, and we also had another speaker who was flying from India but couldn't make it due to some last-minute travel problems. Before we dive into the technical details of the topic, let's take a look at the reason we chose the topic of BLE security. Why is IoT such a hot topic these days? And if you haven't already noticed, IoT connected sensors and applications have taken over pretty much every aspect of our human life. Be it your self-driving cars, wearable devices, sensors, smart home ecosystems, applications monitoring consumer retail habits, and so on. They're pretty much connected with every aspect of our life these days. And with such large use cases, low power consumption and cost are a primary consideration. And also with such large amounts of data flowing back and forth, there's a lot of attack surface and a lot more concerns with security being on top of the list. To name a few of IoT-related hacks that happened over the past year, the Linux Power Rifle hack demonstrated by Runa Sandvik, and also the baby monitor hack, also the wireless car hack that was demonstrated by Chris and Charlie Miller. So let's take a difference. What are the differences between Bluetooth Classic and BLE? Unlike the common misconception, Bluetooth is not a piece of plastic used to answer phone calls on your mobile phone. It is a wireless technology standard used to exchange data over short ranges of distances. BLE, on the other hand, came out as part of Bluetooth version 4.0 and was designed with a focus on low power consumption. And if you take a look at the peak current consumption section over there, it's really evident that BLE is ideal for devices running on coin cell batteries. So let's say smart pay systems, wearable devices, and such. And typical use cases for Bluetooth Classic would be wireless speakers, headsets, and such. Bluetooth 5 would be coming soon and with increased range and speed. And for the purposes of this presentation, there are 5 important modules of interest when we look at the BLE protocol stack. The first one being GAP, or Generic Access Profile, which defines how devices connect and talk to each other. The second layer being GAT, which defines and describes the characteristics, services, and their usage. So when we say characteristic, any data that flows between the wearable device and the application itself is represented as a characteristics. So if it is a heart rate monitor, your heartbeat would be represented as a characteristic or using a characteristic. And SMP is used for exchanging keys, managing, distributing when you decide to use secure communication between wearable devices or wearable and companion mobile application. The attribute protocol defines the rules for accessing data between each application or between devices. And L2 cap layer is your multiplexing layer over BLE. In order to understand how BLE works over the air, there are 2 important concepts we need to look at. One, the connection interval, and second being the advertising interval. Let's take an example to look at this. We have a wearable device, which is also known as the broadcaster, and we have an observer. Typically, the device that has data available would start to broadcast advertising packets, and the device that would like to access this data would be scanning on a preset range of frequencies. So the broadcaster sends out advertising packets at preset intervals or also known as advertising interval. The observer scanning on these preset range of frequencies notices that there is data available of interest and sends out a connection request back to the broadcaster. Now, once the broadcaster accepts this connection, they assume the role of GAT server and GAT client. So GAT being the module we took a look at earlier, and typically the device that contains data of interest is known as GAT server, and the device that would like to access this data is your GAT client. And after the connection is established, the devices communicate between each other. And one other thing you need to notice here is the data flow does not happen on a continuous basis. It happens at regular time intervals, and which is also known as connection interval. It's really important to transmit data using connection interval and advertising interval in order to achieve the concept of low power consumption we spoke about earlier, and which was the whole idea behind BLE. Before we get into how BLE encryption works, we need to understand the pairing algorithms available. So depending on the I/O capabilities of your wearable device and mobile application, there are 4 algorithms you can choose from. Just works, as the name suggests, the connection between wearable devices or peer devices happen without any user interaction. So typically devices with very limited I/O or very limited display capabilities use JustWorks. And numeric comparison is where you would see a numeric value on one of the device, and then the user have to manually compare that it matches the other device you would like to connect to. And there's a yes or no button that you can just click if the values match with each other. Passkey entry is very similar to numeric comparison. The only addition here is it would have input interface, so you would have like a keyboard support to enter the passcode value you see, and then you would proceed with the connection. Out-of-band channel is when you use an out-of-band channel like NFC to initially exchange data, and then you would use BLE thereafter. So, and just to mention, we'll take a look at it later too, but the security of the channel really depends on the type of pairing algorithm chosen. So if you use JustWorks, since there is no user interaction required, it could be susceptible to man-in-the-middle attacks. Now, to take a look at the types of keys used in BLE encryption, or when 2 devices decide to communicate securely, there's a sequence of steps that need to happen before the communication is encrypted. To take a look at that, we have the broadcaster and observer that we saw earlier. So the device that would like to initiate a secure connection sends out a so-called pairing request. Now this has the data, or this has description of the keys that it would like to exchange and the keys that would be used later on in the communication. And it also has information about capabilities of this particular device and so on. And if the broadcaster thinks it is compatible with the device it's going to be communicating, and it supports all these capabilities, it responds back with a pairing response. So here comes our first key of interest, which is also known as temporary key, or TK. The value of TK depends on the pairing algorithm we took a look at earlier. So if it is JustWorks, it would be 0. And in the case of numeric comparison or passcode entry, the numeric value itself would be TK. And in the case of out-of-band channel, the value you exchange using the first protocol would be the value of TK. And a random number from slave and master are then combined together with TK to derive our second key of interest, which is also known as the short-term key, or STK. Now, short-term key is used to encrypt the channel temporarily before exchanging any other keys thereafter. So once the channel is temporarily encrypted using short-term key, there comes LTK, or long-term key, ITK and IRK and CSRK. So LTK is really important if 2 devices go out of range and they come back into range and decide to communicate immediately, And if they don't want to go over the pairing procedure all over again, LTK is really important. So any further communication can just continue securely with LTK without having to derive TK, STK, and so on. IRK is used to enable privacy on wearable devices. So if you use IRK, you can broadcast different private addresses at different intervals, but you could still be discoverable and you can connect to already trusted devices. So that is why IRK is used. And CSRK is used when you want to authenticate the sender of the message, but you do not want to use encrypt or you do not want to encrypt the channel communication. ECDH and AES are just a couple of algorithms that are available as of today for BLE communication. And Core Bluetooth is available for developers looking to enable Bluetooth capabilities on their application. So Core Bluetooth is just an encapsulation of the BLE stack we saw earlier. And it offers various classes, objects to connect to multiple peripherals and also manage the characteristics, transfer the data, and so on. On Android, the support for BLE was enabled as part of version 4.3. And all you need to do is enable those permissions, so Bluetooth and Bluetooth permissions and in your manifest, and you would be able to communicate over BLE or with other applications using BLE. Just before we dive into the problem, just to mention a couple of already known risks. If you're using JustWorks, as we saw earlier, since there is no user interaction required, you could be susceptible to man-in-the-middle attacks. And also, if you take a look at Mike Ryan's research, what it states is if an eavesdropper snoops on your traffic going back and forth during the initial pairing algorithm, even if you decide to encrypt the channel later on, since your initial pairing request is compromised, all your keys used thereafter would also be compromised. So even if you encrypt the channel thereafter, it is not secure. And moving on to the weaknesses, we'll take a look at the fun world of wearables here. And for the purpose of this presentation, we will be looking at fitness trackers and activity monitors. And generally speaking, these wearables come with an associated companion application that run on an Android or iOS device. And they typically use Bluetooth BLE communication to talk with your mobile device or the companion application. And some of the wearables these days can also connect to other peripherals, such as your chest strap to monitor heart rate and pedometer to monitor the number of steps you've taken and so on. And the protocols there are Bluetooth, BLE, and Plus. Bluetooth, not so many peripherals that communicate with wearables these days, but that is a possibility. And your companion application could also be talking to a backend cloud. Now, the use cases for the backend cloud could be user data analytics. So a user can store his data on the cloud backend and process it to coach him better, or multiple features there. The stack is much richer at the backend, and typically you use your network protocols to communicate there. Some devices could also bypass the whole mobile application and directly talk to the cloud backend. So if a wearable device has support for Wi-Fi and such, it can bypass the mobile application and directly connect to the cloud backend, such as your smartwatches. And before we look at the problem, we'll be exclusively concentrating on the highlighted portion of the slide here. So just the wearable and app communication. Now, taking a look at the data that flows between the wearable and mobile application, there's a wide range of data that goes back and forth. And the data coming from the mobile application to the wearable device can be itself in two types. So the first being device commands. Let's say you have a new firmware update downloaded from the cloud and you'd like to push it to the wearable device. You'd have to put the device in a special state or a recovery mode before you perform this action. and you can issue a command for the same. And let's say if you want to change the BLE name advertised by the wearable device itself, you could issue commands to change the BLE name. And there could also be support to display notifications. So wearable devices these days have haptic or LED display, and they could blink depending on if you have a phone call or a text message, or if it is a notification from a social media app, and so on. And the data flowing in the backward direction being all your data from the wearable itself back to the mobile application. Now, this could be your activity data. So let's say the wearable could say if the user is running, biking, swimming, and so on. And also your biometric data, your heart rate monitoring systems could send back your heartbeat and calories, your temperature data. And I mean, it could be connected to any kind of sensors, really. Wearable devices could also be monitoring your applications running on the mobile application itself. So, on the mobile phone itself. So it could be, you could use your wearable device to answer a phone call, or skip a music track, or you could also use it to reply back to text messages and so on. And there could be some weird worrying cases where a notification is sent to the wearable device and it gets bounced back to the phone. Oh, we're getting closer here. Now, let's take a look at a network attacker trying to observe all the traffic going back and forth. Now, as we saw, you could enable Bluetooth security, and all the traffic would be encrypted using your long-term key. So even if an attacker uses tools like Ubuntu and then tries to analyze the traffic, it wouldn't be, I mean, there would be any damage there. So all the traffic is encrypted, we're all good there. But the problem lies here. If you take a look at the way BLE operates today, all the encryption happens, or it is acting at the granularity of the phone and not the mobile application. So if you take a look at a malware application or an application that runs on the same mobile phone, and if it uses the same BLE characteristics, or if it decides to use the same BLE services and the BLE stack, it could have access to all the data unencrypted in plain text, similar to your legit application. And the malware application could also issue commands back to the wearable using the same message header or the same format as if a legitimate application would. Now, that is really the punchline here. All applications on Android and iOS can subscribe to the Bluetooth services and get access to the data on the same Bluetooth channels as the legit application. Now, on Android, it's fairly simple. On Android, all you need to do to enable Bluetooth communication is define those permissions. And the screenshot you see here is a clip from the developer documentation. So all you need is Bluetooth admin permission, and the other abilities granted by this permission should not be used. Yes, all our malware applications obey our rules, and we just trust it to behave as dictated. And on iOS, you have well-documented classes, objects, and so on to communicate using BLE interfaces or Bluetooth interface. Let's take a couple of examples. So we've analyzed a bunch of wearable devices to demonstrate different use cases or different scenarios of how an attacker could exploit this vulnerability. And the first class of wearables we analyzed were fitness trackers, so general fitness monitors and such. They use BLE, not Bluetooth Classic. And the source code for the applications we analyzed is proprietary. It is not available. And but there was fairly good amount of data available publicly for us to recreate the format of messages sent from the legit application back to the wearable device. And I mean, even the malware application was fairly simple. We created a malware application that scans for GAT characteristics. So GAT characteristics being the data or the module we saw earlier. So all the malware app would do is scan for the characteristics and do a bunch of rewrite operations. And then we try to analyze the data that was collected by the malware application. Let's take a look at the demo. The Legit app here is running in the background. It is not shown. The screen on your right side is the malware application. So it is just trying to scan for GAT characteristics and then trying to perform a bunch of read-write operations. So we're trying to connect to the device. And you need to remember that while all this is happening, the Legit application is connected to the wearable device. So there is already an active session going on the same phone as the malware application is installed. And the screen on your left is Lockat. So we're just analyzing the data collected by the malware application. Initially, we just noticed a bunch of random hex values. And when we took a close look at it, we realized that it was the steps, calories, and the heart rate that was available from the wearable device to the Legit application. So we quickly wrote a parser to convert this data, and we indeed realized that it was the steps, calories, and heart rate that was being collected by the malware application. I mean, it's all the data that was really available to the Legit application at the same time. So we just tried to simulate more activity. We were trying to spin the wearable and run and so on. So this is all the live data that went on there. The second class of wearables we analyzed were a little more complex. So they had capabilities like Wi-Fi. So they could talk directly to the cloud backend instead of channeling through the mobile application itself. Now, when we ran our malware application on and tried to sniff data from these kind of devices, we couldn't really notice much. I mean, all the threads that were associated with app being the channel to talk to the backend were not observed in this class of devices. The next class of wearables that we took a look at were even more interesting. So we tried to run the same malware application and try to listen to the communication, try to access the data. Initially, we were not able to get anything. We paused here and took a look at what the Legit app was doing. And it did turn out that the Legit application had thought of security. I mean, the designers of the application had thought of security. And as part of the initial handshake and connection, they were using authentication. So the Legit application would authenticate itself during the initial handshake with the wearable device. But it didn't stop us. It just took us a little more time. What we did was we tried to analyze the capabilities available on the Legit application. We tried to replicate it, but stripped away the authentication part, and then try to, or we waited for the Legit application to connect with the wearable, and then we fired up our malware application. So let's see what happens here. So on your right is the Legit application. It's trying to scan and connect with a wearable device. And to your left is the Minicom logs and basically the serial logs. We took a look at the commands available from the Legit application. There's a reboot, power down, and factory reset. So we go ahead and give a reboot. And notice the logs there, the device reboot. So far so good. Now we fire up the malware application on the same phone and we issue a reboot command. And voila, the device reboots. So the moral here is partial security does not help. You would have to authenticate, or you would have to protect every message that goes from the mobile application to the wearable device. I mean, you must be thinking, this needs a malware application on my phone. We are all security professionals. We are all paranoid by profession. That would never happen, and so on. Really, I mean, the risk here is low, but the impact is really high. There are tens and thousands of applications these days on the App Store and Play Store, and it's really hard for someone to pinpoint a malware application from this lot. I mean, all that would, all the malware application would need is Bluetooth permissions, Bluetooth admin that we saw earlier, and it would be able to access all the data available to a legit application. And there are issues of confidentiality, right? So wearable devices are very different from your traditional phones. So they would be staying with you, walking with you, they're with you everywhere you go around. And devices that have GPS capabilities enabled, they have access to user location data. So they would know your office address, home address, and very fine-grained details. They would also have access to your heart rate data, temperature data, calories, and so on. There was also an interesting case where someone just shared their activity data on their social media page, and someone just commented saying, oh, you might be pregnant. So it's really dangerous to disclose all this data or to have this data compromised. And there are also cases of integrity and availability. So an attacker could launch a permanent DOS attack, or they could change the name of your BLE device and then result in your device not being able to connect with the legit application. Or worst, they could put it in a recovery mode, and you would have to take it to the service center to have it recovered. And also, if you are a hot young startup trying to make a dent in the wearable market, a very small article that explains how crappy your security is I mean, it's really harmful for your business or brand names thereafter. And it could also be a board risk where a malware application could just be released into the App Store or Play Store, and it really doesn't need to do anything with the wearable device, and the attacker could result in a mass infection. So what do we suggest to fix all these issues? Over to Chandra.
Hello. Thanks, Kavya. So let's see what are, before we dive into the design or the solution that we are proposing, let's see what are a few objectives and the non-objectives. So here the objectives, what are we trying to prevent, or what are we trying to protect it from? So as you saw in the Kavya's presentation, that the malware application is able to send the commands like factory reset, or even it's capable of changing the device name and or switching the device into the recovery mode. Or the vice versa is the applications are able to sniff your sensitive data, like activity data or anything, or the application specific feedbacks or inputs. So these are the objectives that we are trying to solve here. And the other assumptions and the non-objectives are like, we are assuming that always the legit application is the one that pairs to the wearable device for the first time. So that's the out of the box experience. And a few non-objectives are, since the rooted or the jailbroken phones are out of scope for us, because since user has or the attacker has the complete control over the phone, no matter what security put into the rooted phones. And also we are not considering all the other vulnerabilities that exist on the phone or the apps that can break the sandbox model, because we want to completely trust the host operating system sandbox model. And so the other non-objectives are the rogue applications on the on the mobile phone trying to pair to the wearable device before the legit application does. And also the man-in-the-middle attack during the BLE pairing is not an objective for us. So let's see the overview of what the mitigation that we are proposing here. So as you saw in the earlier presentation from Kavya, that the BLE pairing is from the BLE stack on the phone to the BLE stack on the wearable device, but nothing prevents from the applications that's running on your phone or talk to the wearable device. As you can see that the same BLE channel is available for the rogue application as well as the legit application. So the device on the other side doesn't have a capability to differentiate what are the legit application versus the rogue application. So what we are trying to suggest here is have one more layer of pairing that is from the application to the device, so that whenever the application first time talks to the device, that's when it initiates its own pairing process. And those are the designs that we're going to see in the next few slides. But here, before that, there are few considerations, since there are different class of wearable products that are available in the market. Since, like, a single wearable product, a wearable is able to talk to multiple phones, or a single phone is able to talk to the multiple wearable products, or it's multiple phones versus multiple wearables. So here, let's dive into the different designs that we are proposing. So the first design is very simple, where when the wearable device doesn't have a much computing power and the application side doesn't, the developers doesn't want to have a cloud support, so they can go with this kind of a design where the application on the phone, the legit application on the phone generates a random key, or you can call it whatever you want, and then which exchanges the key to the wearable device during the first pairing, and then they use those both keys, the key on for the secure communication, and that's so that none of the other applications like rogue application would be able to talk to would be able to sniff to the device and understand what the communication is all about. And we will be seeing this same demo at the end. So now the second class of design is where you have a cloud services available. I mean, if you cloud backend available for your application. So now you say, like, the application user has to log into the application to authenticate himself. So now how are we trying to protect here? We doesn't want to use an password as a secret key for the secure communication with the wearable. So hence what we propose here is have a separate kind of a mechanism where the user can provide his own secret key or the PIN number that can be used for a secure communication. So in this way, the complete control is with the user. So now once the key is being entered, then again they use the same key exchange mechanism with the wearable device, and then once the pairing happens, and then the secure communication begins. And if in this case, since the user can have multiple phones with the same account, so in that case, user doesn't want to use a different PIN for different applications. So if you for the same account, so in that case, once the key is being entered for the first time, then it's being uploaded into the backend, and during this successive login authentication mechanism, the backend delivers those keys, the same key to the application, and then the application can use it for the secure communication. Since the device that he's talking to, it's the same device which already had a key exchange, and it has the same key available on the device. So then they can use the same key for the secure communication. So now here, if the users really doesn't want to have the keys that needs to be uploaded in the clear text, or if if the developers decide not to request a key from the user, they can generate a random key on the application itself and then exchange that as a for the secure communication. And then they can upload the encrypted blob of the key using the password of the user, because since again the user has the control on the key that is being generated. So now as part of the login process on the other application, the backend delivers the same encrypted blob, and because since the user has logged in, it can be decrypted on the application side, and then use the same key for the secure communication. So Now, this is one of the solution that we're calling universal solution due to the lack of word that we want to put in this. Because since all the problem here is, since we see is because the operating systems like Android or iOS doesn't provide any solution to secure the channel from the application to the device. If they, in future, if they support, so then we don't need to have any kind of other solution, since the operating system provides an might provide an API. And then we can use those same APIs as we use the other APIs available on the Android or the iOS. So when you're talking about these Bluetooth devices, so there are chances of losing a key, because since the device can go out of range from on the Bluetooth, and the device, it's a chances of device getting reset. And again, the user can pair it to the device from the settings application, as most of you are aware of how to pair it. So at that time, because since your application is not the one that's talking to the device for the first time, rather than the operating system is the one. So now in this scenario, the application is already available, which has a key, but the device doesn't have a key. So that's one of the corner cases. And the other corner case is when the application is uninstalled and reinstalled. So that time the application loses all the storage, whatever from its private storage. So in that case, the application loses the key, but the key is with the device. And the other one is like, when the rogue application is trying to pair it to the device when the legit application is already paired. So to prevent these things, so we say, like, we call this as a post out of the box experience flow. So whenever the application exchanges the keys, or when the device goes out of range and comes back in the range, or the application is uninstalled, anytime for the application is talking to the device before when the disconnection happens. So they have to challenge each other, saying that, hey, am I talking to the right application, or am I they can follow any challenge response mechanism, as well as the device does the same thing, so that the application can respond back saying that, yeah, I am the one who you are looking for. So in these cases, there are chances of, like, in the examples that I spoke earlier, because when there is a key mismatch happens, the application should be able to alert the user, so that the user interaction is needed at that time to put the device into the reboot mode or reset the device. So now when the challenge mechanism response is success, now both the parties trust each other, and they both have a key. So they can use this key to encrypt the data, like for the device can encrypt the data, the activity data, or the heart rate data that is being sent from the wearable device. Or if you can use the encrypt or use the authentication to authenticate the commands where the application is sending. So in that case, the wearable will authenticate the command before it reboots the command. As you saw in the demo now, the malware application was able to send the command and device reboots. So with this mechanism, so you can control the device, so that the device, the communication is not available to the applications running on the phone. So let's, in this demo, we will be looking at an application which has already the design that I spoke, the first design, where the application generates the key, and then it exchanges the key with the wearable when it is paired for the first time. And also we have a demo malware application which tries to read the data and see how it tries to interpret the data. So here, if you see this, so this is our legit application where it's already paired. The only thing is it's trying to connect again to the device, because since during the for the first time when the device is paired, that's when the key exchange has happened. So now both the device on the other side as well as the application have the same key. So now all the communication and the commands that the device is able to send are encrypted and authenticated. So only the application that receives the messages can decrypt and display it. So here the class of product here is like the notification that arrive on your phone is being sent to the wearable device, and the wearable device bounces back the same message, same notifications to the phone, which is in encrypted format. So now here there is a notification on the Facebook Messenger, which is being given to your wearable device by the Apple or the Android operating system. So now you can see there is a little console we have built where you can see the actual, we can see the exact notification that you received here. And so now let's fire up the malware application, which is also connected, but the legit application is also running on the background because that's what the session is being maintained. And now you can see the status here at the top that the connection status is yes. So now again there is a we will see the notification, a new notification received on your Facebook Messenger, and this message is available on the wearable, and which is and then the wearable is sending you the encrypted notification back to your phone. So now, since as you can see here, this notification is in some gibberish format, since it's an encrypted data that we are receiving from the wearable device. Since the malware application doesn't have the key, it's trying to display whatever it's been received, and then now the malware, the attacker couldn't understand what exactly the message is. So now let's go back to our legit application and see if we are able to interpret the same message and in the clear text. So now, because since the legit application has the key, it's able to decrypt the data and display it in a plain text. So the summary here is, because basically if you want to push your malware application to the phone, there needs to be a user intervention, because since it's not an easy task for an attacker to push an application without user consent. So even though it's a medium risk, but still the impact of the vulnerability is high, because since the malware applications can read your personal data, like heart rate or GPS data that's sensitive. And even the impact is even more severe when these wearables are used in the financial or the security space use cases. For example, when you have an Apple Watch, you unlocking your Mac. So in those scenarios, it will be severe impact. And assuming that protecting from the network attackers is enough, but that's not the case, as we saw in the demo. And now, since there is no solution that the operating systems provide, we as an application developer or OEMs has to put in a lot of effort by adding an extra layer of security from the application to the device communication. So that's the end of our talk. So thank you all for joining us. And if you have any questions. Thank you.